section 5.2, which is called volumes of revolution, disk and washer methods. We have seen that the area problem can be solved using the antiderivative of the function. But it turns out that integral also can be used when you are interested in volumes as well. And today we'll discuss one of such examples. So in this section, we will learn how to find volumes of certain solids, which are called solids of revolution. So suppose you have some function f of x, which is continuous on some interval ab. And let's consider the region under this curve. If the entire region is rotated about the x-axis, we'll obtain what is called solid of revolution. And if our initial region was approximated by rectangles, then the approximated volume is obtained by the rectangle which is rotated about the base. That's what we see on the picture. This is our initial rectangle, and then we rotate it. We'll get a cylinder that has height dx, and the radius will be value of our function at that point. But let's recall what is the volume of a cylinder. So say this is height, and the radius is r. Then the volume of such cylinder will be, so it's area of the base times height. But my base is a circle, and we know that the area of the circle is pi times radius squared times our height, we denoted by h. So this is volume of the cylinder with the radius r and height h. And coming back to our picture, this cylinder has height, which is dx, and the radius, since we rotate around x-axis, is just value of our function at that point, x. Sorry, we get that the volume of this cylinder thus will be equal to pi times radius, which is f of x, squared times height, which is dx. And then we need to sum up all such cylinders in order to obtain the whole volume. And again, as we remember, summation corresponds to integration. So we get integral from a to b of our typical element. In this case, it will be pi times f of x squared times dx. Or I can write it as integral from a to b, and this is my volume, pi y squared dx. And this is what is called the disk method, because our typical element is in fact cylinder or disk. And let's do some example. Let's calculate volume of a sphere of radius r. So how to apply this disk method in our case? So let's consider half of the circle of radius r. So this will be my r, this will be my minus r. So it is my semicircle. And we can obtain the whole sphere if we rotate this semicircle around the x-axis. Or in other words, a sphere is a solid of revolution that can be obtained by this semicircle rotated around x-axis. And so what is our typical rectangle? Again, repeating the same steps that we did, here is my typical rectangle that will correspond to the disk when I will rotate it. So it has base dx, while the height is f of x, or it will be, what is the function that corresponds to the semicircle? It is square root of r squared minus x squared. Because remember that the equation of the circle of radius r and centered at the origin is x squared plus y squared is equal to r squared. And thus, y is equal to plus minus square root of r squared minus x squared. And if I'm interested in the semicircle which is above the x-axis, then it will be just plus square root of r squared minus x squared. Thus, this rectangle will become the corresponding cylindrical disk. By the same reason, as we have seen, the radius of this cylindrical disk will be f of x, but in our case, f of x is square root of r squared minus x squared, and thickness, which is just dx. And so the corresponding volume will be, so it's pi times r squared, or f of x squared times dx. But this is only volume of our small cylindrical disk, and then we need to sum up all such disks. So we get, again, integral from a to b, but our a is minus r, while the right-hand point is r. So we have integral from minus r to r, pi f of x squared, but our f of x is square root of r squared minus x squared, so it becomes r squared minus x squared dx. And that should correspond to the volume of a sphere of radius r. And the rest is quite simple because I need to integrate polynomial. So first of all, r is a constant. So when I integrate it, I will get just r squared times x. And when I integrate x squared, I will get x cubed over 3. And by the fundamental theorem of calculus, this volume will be this function substituted from minus r to r. So I'll get pi. On the upper limit, I'll get r cubed minus r cubed over 3. And on the lower limit, I'll get minus r cubed minus, so it's plus r cubed over 3. And so it is the same as pi 2 pi r cubed minus r cubed over 3. And so it is 2 pi times, if you do the common denominator, it will become 2r cubed over 3. Or finally, it's 4 pi r cubed over 3, which is volume of a sphere of radius r. First application of our disk method. The same story happens when you have two curves, f of x and g of x. The typical rectangle will be this one between two curves. And if you rotate such rectangle, you will obtain not a disk, but a washer, because you will have empty space between x-axis and g of x in this case. You will get a picture like this. You will get a washer. But you can repeat the same tricks. So this is my f of x, and this is my g of x. And this is my washer that I consider in the middle. So what is the volume of the whole disk? It is, as we discussed, pi times the radius of the disk, which is outer radius, f of x squared dx, while the volume of the hole in the center will be pi times g of x squared dx. This is volume of the washer. So it's your typical element, typical washer, and thus the whole volume will be integral from a to b pi f of x squared minus g of x squared dx. And this is called washer method. Okay, let's do example number 2. So suppose you have line y equals x plus 3 and the parabola y equals x squared plus 1. If you graph it, you see that there is bounded region, and we want to find the volume of the solid of revolution formed by revolving this region about the x-axis. This is my region, and I want to rotate this region around x-axis and find the volume. I know the general answer that the volume will be integral from a to b f of x minus g of x squared. So my top function, as I can see from the picture, is x plus 3. And the function which is below is x squared plus 1. So what I'll get pi. Then I have function which is the top one, so x plus 3 squared. And I should subtract the bottom one, which is x squared plus 1 squared dx. But I need to find my limits. And how can I do that? I see that my limits are exactly the intersection points of these two curves. So what I need to do, I need to solve the following equation, that y1, if I call it y1, this is y2, should be the same as y2. And I'll get that x plus 3 is equal to x squared plus 1. And if I simplify it, I'll get x squared minus x minus 2 is equal to 0. Or I can factorize it and get that it is x plus 1, x minus 2 is equal to 0. And thus either x is equal to minus 1 or it is 2. And that gives me these two coordinates, which in fact are my limits of integration. So from minus 1 to 2. And here I used this washer method. And the rest is straightforward. I should expand my function, my integrand, and get that it is integral from minus 1 to 2 minus x to the power 4 minus x squared plus 6x plus 8 times dx. And so I have just a polynomial that I need to integrate, so it's easy to calculate the antiderivative and then use fundamental theorem of calculus to obtain the following, that it is pi, then you have minus x to the power 5 over 5 minus x cubed over 3 plus 6x squared over 3 or over 2, which is 3, and plus 8 times x. And substitution from minus 1 to 2. And if you substitute, you will get that it is 117 pi over 5, which is approximately 73.5. Okay, let's do one more example. Example number 3. Find the volume of the solid obtained by rotating the region bounded by x equals square root of y equals 4, and the y-axis. And I rotate about y-axis. So what do I have? I have the following graph. Y, so I have x is equal to square root of y, or I can think that y equals x squared, where x is positive, non-negative. Then I have y equals 4 and y-axis. So this is my region. But this time, I want to rotate about not x-axis, but y-axis. In this case, we need just to interchange the roles of x and y. And so we need to draw a typical element, which is not vertical rectangle, but rather horizontal one. That we also did when we discussed areas of function, which is expressed as a function of y rather than a. So here's my typical rectangle. Now it's horizontal one. So its thickness is dy, while its length is x of y. That we also discussed. And after I rotate about y-axis, it will give me disk. Now it will be, again, horizontal disk with radius, which is x of y, and thickness, which is dy. And so the corresponding volume of a typical disk will be thus pi x of y squared times dy. And then I need to sum up all such small disks and obtain that the total volume of my solid of revolution will be integral, which is the same as summation, pi x of y squared dy. And what about the integration limits? So first one is again simple to find, which is 0. And second one, or the upper limit, is also clear because it's just 4. Again, since I'm integrating with respect to y, I need to find my limits, which are y coordinates, not x. But my x of y is just square root of y. So in this case, I get that it is pi integral from 0 to 4 square root of y squared dy. And so it is pi integral from 0 to 4 y dy, or it is pi y squared over 2 substitution from 0 to 4, which is 8 pi, or approximately 25.1. And next example, example number 4, shows that the washer method, when you have two functions, can be also done in case when your function is expressed in terms of y. Revolve the region bounded by function y, which is x to the power 2/3, x equals 8, and the x-axis. You revolve about y-axis. So each time you should be careful what is the corresponding axis. Either you rotate around y-axis or you rotate around x-axis. That will give you different answers. Again, let's draw a picture. So I have this region, but again, I want to rotate it around y coordinate. If I slice it, it will look like this. But if I rotated it about x-axis, the picture will be completely different, because then the slice will look like this. So you see, indeed, volumes are very different. Since I'm rotating about y-axis, I should consider horizontal rectangles. So this is my typical rectangle. So its thickness is dy, and since I'm interested in the volume, you will get a washer with outer radius, which is 8, and inner radius. So since I'm measuring the x-coordinate length, so y equals x to the power 2/3 is equivalent the equation x equals y to the power 3/2. So the inner radius thus will be y to the power 3/2. I'm interested in x coordinate, so I need to express x in terms of y. And thus, by the washer method, my volume of revolution will be integral pi, then I have outer radius squared minus inner radius squared, so it's y to the power 3/2 squared, and thickness of my washer is dy. So indeed integral with respect to dy. And my limits, lower limit is 0, while the upper limit should correspond to the point x equals 8. So this is 0. And how to find this value? I know that my y is x to the power 2/3. And when x is equal to 8, then my y will be 8 to the power 2/3, or it is cubic root of 8 to the power 2. Or it is 2 squared, thus is 4. So this upper limit is in fact 4. So I should integrate from 0 to 4 my function. And what I'll get? I'll get pi integral from 0 to 4, 64 minus y cube dy. And again, it's easy to integrate, and we'll get that it is the same as pi times 64 y minus y to the power 4 over 4, substitution from 0 to 4. And if you substitute, you will obtain that it is 192 pi. Again, we can generalize disk method and washer method in case when your function is given in terms of y and when you rotate around y-axis. But just to show the difference, let's do the same example, but revolve this region about x-axis. So I rotate around x. Still my region is this one, but now my typical element is vertical rectangle. And this vertical rectangle has base dx and height, which is f of x, or it is x to the power 2/3. And so there is no washer because there is bottom function is just x equals 0. So my volume v tilde will be integral pi, and so this rectangle, after I rotate it around x-axis, will correspond to the disk with radius f of x, so x to the power 2/3, and thickness dx. And thus volume of this disk will be radius squared, f of x squared times thickness, and I sum up all such disks from 0 to 8. And so what I'll get? I'll get pi integral from 0 to 8, and then I'll have x to the power 4/3 dx. And so it gives me pi x to the power 7/3 divided by 7/3, substitution from 0 to 8. Or it is 3 pi over 7 times, so at 0 it gives me 0, 8 to the power 7/3. And 8 to the power 7/3 is again cubic root of 8 to the power 7. So I obtain that it is 3 pi over 7 times 2 to the power 7, which is of course not the same as the answer that we got before. So they are completely different. And also we can see that in the first case, I had to use washer method because there was this gap between y-axis. While here, when I rotated around x-axis, there is no gap between the x-axis and my region. So I used just the disk method. So they are completely different.